All right. Good morning. You can hear me and see my screen? Yes? Great. All right. So my name is Bob Tawa. I'm the DKIST Data Center Project Manager, and I'm going to be giving a talk about how we manage our data. Okay, so just as a quick project overview, I'm not a scientist, so I'm going to go through this relatively quickly. DKIST is at the moment the most advanced and very complex solar observatory. It's got a 4-meter aperture with a wavefront correction system. It's an off-axis design, which means that there are multiple mirrors. I think there are 7 or 8 mirrors in the light chain. And at the bottom of it all down here is a Coude table, which rotates and has 5 separate instruments, some of which can be used at the same time. So we get data from 5 instruments as we take observations. The 5 instruments that I'm talking about are visible spectropolarimeter, VISP, a visible broadband imager, VBI, a cryogenic near-infrared spectropolarimeter, CryoNIRS, something similar, diffraction-limited near-infrared spectropolarimeter, DLNIRS. Those are the 4 that are currently active on DKIST. The visible tunable filter is currently being integrated and will probably be starting to put out data sometime in 2026. The kind of images that we get, you can see there on the right, they're very detailed images of the sun and as well as spectra. So DKIST is sort of new in solar science, in that previous to DKIST, PIs would go up to the observatory, to the telescope with their hard drives and take data and take the data home with them. In this case, we are service mode. We have proposals that are submitted on, I think, a bi-yearly basis. And for those proposals that are accepted, we take data for the PIs and as much as we can, obviously, depending on weather. And then we give the PIs the data. They have a 6 months sort of embargo period, proprietary period, after which the data becomes public. So in terms of the data center itself, we are responsible to receive, process, store, and curate the data. Roughly petabytes per year for 40 years. It's a 40-year project. There are millions and millions of files that come in on a yearly basis. The telescope itself is in Hawaii, and it observes during the day in Hawaii time, obviously, and batches the data and transfers it to the data center in Boulder, Colorado, where I am. My team is fairly small. There's only 10 of us that deal with this data. 4 of our team are strictly calibration engineers. They are scientists who I'm slowly turning into software engineers. And in order to deal with that much data, obviously, we need a lot of automation, which we've implemented, and we have implemented a great deal of system visibility. We need to know when something is going wrong immediately. Otherwise, things will just pile up. So everything is automated. All the data movement and the pipelines are automated. Monitoring is automated. Testing is automated. It's we probably run the testing system, I think, probably twice a day. Every time we have a release, we release on average twice a day. So yeah, that's sort of the way we keep on top of it with a small team. So what is our responsibility? We've got to be able to store the data, augment the data with more data and metadata. One of our key requirements is we can't lose any of the raw data. We have to keep it in perpetuity. So we periodically audit our stores to make sure that nothing untoward is happening. Obviously, we have to be able to search and filter the data on a number of axes. There are currently 19 separate filters available on the portal that you can filter on. So in terms of the architecture itself, when we built the system, we obviously took a look at the illities, the architectural illities, scalability, maintainability, so on and so forth. As you can see, most of these on the left are some of the higher level services that we provide, and whether they need to be scalable, maintainable, extensible, so on and so forth. And the way we implemented this architecture is essentially, it's a microservices architecture. On the outside, out here on the outer ring, are the major services that use services on, in this ring out here, which use services in this ring out here, and they're all color-coded to tell you what services are being used. In total, we have probably around, I want to say 50 services that we maintain, as we go. Occasionally we add, but for the most part, it's been pretty steady for the 3 years that we've been in operations. So how does data come to us? So at the beginning, the instruments observe and produce science frames. There is software that we are not responsible for up on the summit that creates, stores the relevant metadata in a header database. It stores the images. It fitsifies the whole package. And over here, there are some instruments that make a lot of relatively small files. And this is something that we learned using Globus, is that it works great on large files, not so great on a lot of small files. So we asked them to tar it up into tarballs about 250 megabytes each, and that dramatically improved the transmission of data. Prepares the manifest and submits the transfer jobs to Globus, and then Globus takes care of the transfer. So why do we use Globus? We receive data from the summit to the data center. It does all of the verification, all the checksumming. It routes the science, then we route the science data, route the transfer manifest data. We ingest the science data, ingest the transfer manifest data, make sure everything is right. We have, if anything wrong happens during the transfer, for instance, the FITS spec isn't followed. Keywords aren't there that should be there. Things like that, they go into a failure bucket, and we look at them manually. Our task is to make valid science data received at the data center searchable by an authorized agent within 10 days. So what happens? At the summit, there's a transfer node, which initiates the transfer. Again, Globus takes care of the transfer. We have an endpoint down in Boulder at the data center. We have a Ceph connector, which essentially stores the data. And, we monitor all of the events that are happening. We can see the transfers as they are happening, see if there's anything slowed down or not working correctly, and we can take care of it. The data that's transferred from the summit follows an ICD. We have an ICD with the summit software and is packaged up in accordance with essentially this schema. There's a control, which contains the manifest. It tells us what files are going to be transferred. The actual files that are going to be transferred, there's a camera, which we actually have never used and will probably go away in the next version of the ICD. And then we have an archive, which is new, which contains the tarballs that I talked about recently. Every FITS file that is transferred has a unique name that sort of identifies what experiment, what observing program, so on and so forth. It follows, like I said, a spec, which we call spec 122. And as they come in, they come into an inbox bucket in the DC object store. So what happens to the data? What is the data lifecycle? The raw data is produced by the telescope. Once it is transferred and known to be transferred, it is deleted at the summit. They don't have that much storage at the summit. They have enough essentially for a month if for whatever reason they can't transfer it, but that's it. Once the data is ingested by the data center, we store it permanently in a Ceph bucket. It's immutable, and it is also backed up to AWS Glacier. That's our backup solution. The level 1 that we create at the data center, which is calibrated data, we store it as mutable data because we can change it. It is not backed up. There may be different versions because we reprocess depending on if it needs to be reprocessed. We haven't actually had to reprocess in this paradigm yet, but we do have a process where if we have a reprocessing event, we reprocess, keep that data, keep the previous version of the data, and then delete anything older than that. And when I say delete, we delete the science frames that we have previously created, but we keep the record of that data set having been there. So in terms of processes, the data transfer happens here, and then it gets routed. If it's packaged data, in other words, tarred, it gets untarred, goes back into a data receipt process. Transfer manifest data goes to a transfer manifest ingest service. Science data goes into a science data ingest service. Anything that happens that is wrong goes into a failure management service. We also have this filter manifest ingest. This was sort of an add-on to the system because some of the data that we were supposed to get that was supposed to be processed on the summit was not processed on the summit, and they wanted us to filter it off to send it somewhere in Boulder to be processed, not by us. So we tacked this on. This just goes to the sort of extensibility of the design. So what do? We verifiably receive the data from the summit. A lot of that Globus takes care of. We categorize the data that we receive into science data, transfer manifests, or tarred files. And then each goes to its appropriate service, if you like, and gets stored in the appropriate data store. And in any case of failure, and we have had them, for things that didn't follow the spec, or we've never had this happen, but things that don't follow the spec, we put it in a failure bucket, we investigate it, and we tell the summit, hey, something was wrong with this data, resend it, or fix it and resend it. As I said, transfer is handled by Globus. Great thing about Globus, it manages the authorization authentication. We have in the data center, from a security perspective, makes it a lot easier on us. We have no PII. All we know is the Globus credentials. We don't care about the size of the transfer. They complete the transfer for us. If there are any interruptions, and we've had a lot from the summit because occasionally there's bad weather up there that takes out the line. It recovers immediately when the line comes up. It does the verification, and it lets us know success or failure. And we can parallelize to maximize whatever bandwidth that we have. So it's, I can't say enough good things about Globus. This is sort of another slide that shows what we do. We route, we identify, and depending on whether it needs to be filtered, is it a fits, is it a manifest, it goes to the right service, if you like, and we go from there. So we filter out. We, as I was saying, the filtering was not part of the original design. The VBI data was supposed to be processed on the summit and then deleted. And we were going to get about 1/80th of the original size of the raw VBI data. VBI data was never supposed to be reprocessed because it couldn't, because the raw data was going to be deleted at the summit. As it stands now, raw data is currently diverted to the data center, and we divert it further to a scientist who does the processing on his own machines. We were never supposed to get this much data, and because of that, it caused a lot of issues with manifests and counts, issues with routing. Now we have to re-ingest the data when the scientist is done processing it. So it caused a fair amount of, I don't want to say upheaval, but this was supposed to be a temporary process, which is now in the process of becoming permanent. So at this point, we are starting a design where the data center will process the raw data and make it as though it were like every other instrument. So the transfer manifest tells us what is being ingested, what should be ingested. We use it strictly for counts. We don't care about the names or matching up the names. We just say we're supposed to get 2 million files, and we count as we ingest the files. The data ingest process verifies the fits. We make sure that everything that's supposed to be there is there. We validate against the schema, and then only when it is validated do we create an inventory record, which includes the frame headers, the location of the files, where it is in the bucket, and the date of ingestion. And then we increment the counter to make sure that it is counted against the manifest. When we get to processing, and I'm not going to do a lot of slides on this, essentially what we have are recipes. The recipes include the input data set, in terms of the observations, the calibration data, parameters that are unique to the actual instrument, and general DKIS parameters, mirror parameters, things like that. Once we have that recipe, we send it to Airflow, which is our workflow management system. It runs the recipe, and the VISP recipe is essentially a set of tasks, acyclic graph. It does all of this. We can monitor it. We take a look at it. We make sure everything runs. And this is all done automatically. And once that is done, the level 1 data is stored again in the Ceph cluster. A inventory record is made, and it is immediately available on the portal to the PI. So talking about the inventory, what is it? It's a detailed catalog of all the science data assets currently held. It is designed to help data center personnel, scientists, and users quickly find the most appropriate data for their purpose. So what do we have in terms of storage structures? We have an object inventory. It catalogs all of the objects, all of the big things we have in the Ceph cluster. This is implemented on a Mongo NoSQL database. The frame inventory stores a copy of the FITS headers, which are essentially JSON documents, which we made into JSON documents that are indexed for easier search. It stores the path of the frames, and there's an object inventory for other objects that are not necessarily FITS frames. We also have a search support database, which is implemented in Postgres. It's a SQL database. It stores all of the data required to perform search and discovery of the level 1 data across those axes that I was mentioning earlier. And we have a support database also implemented in Postgres that stores all the metadata required to allow the processing of the level 0 data, and stores metadata related to the creation of the level 1 data, provenance, what recipe, when it ran, what version of the software, so on and so forth. So getting to the object inventory, science data is big both in volume and counts. The data frames, as I said, are stored in the CEP object store. The location is stored in Mongo. The inventory component enables the discovery and select metadata analysis without the overhead of full frame retrieval. So we can take a look at the FITS headers and do things with the FITS headers, in terms of searching and so on, without having to retrieve the entire, the big files. It stores the frame inventory as documents in a Mongo database as frame documents. There's one per FITS file in the object store, and the entire FITS headers are also copied into a document. There are also other documents, generic object documents. We also use, while we use FITS as it comes in from the summit, we also package the data up with in the advanced scientific data format, which is a newer format, which makes it easier for us on the back end on the user tools, which we also have created and are downloadable by scientists. We can use the ASDIF format to sort of manipulate the data in ways that FITS does not allow us to do. There's also a movie. We make a movie of the data, and when we process the data, we also attach to it a quality report that is that goes with the data sets, and also large parameter sets that may have to do with either the telescope or the instrument that is needed for level 1 data processing may also be in the object store. Search support, it's a relational database in Postgres. It is strictly used for discovery of data, its quality, and any related embargo enforcement. As I said, PIs have a 6 months grace period where they have exclusive access to the data, after which everybody has access to it. Database queries are essentially facilitated by a REST API, which can be used, which is used by our portal, it's used by our user tools, and can be used it is available to the general public to be used in software that they may want to write. Search support database places metadata about the frames data sets in a searchable database. It allows the creation, addition of data level 1 metadata, including from other sources, operational tools, things like observation descriptions that came from the proposals, who's allowed to access and for how long. For instance, PIs get 6 months, but PhD students get 1 year in order for them to be able to finish their thesis. The provenance, pipeline version, date of creation, what the entire bolus of level 0 data that made up this level 1 data. Allows internal and external entities to perform research, allows the data center to perform periodic audits. This is how we audit our holdings, and allows, for instance, user tools to download metadata, fits headers, without having to download frames. We use a GraphQL format to in our API so that we work around the REST downsides. It makes it a lot easier to search for data. It abstracts the data models from all of our databases and our services. So this has been a huge help as well. Distribution. We have essentially 3 ways of distributing the data. This is our portal. As of, I think, yesterday, we had 1,921 data sets. Over on the left, you can see some of the filters that we can filter this data on so that people can reach their data as efficiently as possible. On the left over here, you can see this data set is essentially restricted. It's, unless you have PI credentials, you are the PI, you cannot download it, whereas this one down here, you can download. As I said, we have an API. If you want to write your own code to search our database and download our data, you can use the API. And then we have a set of user tools that we created that you can download. They're Python user tools that allow you to work with the data and analyze the data in various ways, as well as download the data to wherever you want. As I noted, we have a small team, and observability into the system is a huge thing for us. We are actually on our second go-around on observability. And, just to give you an idea of what it is, it's the ability to understand the internal state of the system. We use external outputs, logs, metrics, traces. We collect all of that and visualize it. We have dozens of dashboards that we can use to see exactly what is going on, both in the applications, in the services, on the hardware, everywhere. If we did not have this, we would not be able to keep the system up. So far, we've been up for 3 years without a second of downtime. We would not be able to do this without this observability. So, as I said, we're on our second go-around, and we are using mostly Grafana to provide this for us. We have Loki, Tempo, and Mimir for various things, traces, metrics, logs. We visualize with Grafana, and then we have an alert manager, which we use Prometheus for. We have alerts going on email, Slack, messages if anything is happening that should not be happening. So what do we have? We have logs, which are structured or unstructured text records of events, can be out-of-the-box applications. Things come with logging, or we have logging that's purpose-built for instance, in our code. We use Python Log Guru to do that. Metrics and telemetry, this is mostly on the hardware stuff, core system functions, CPU, memory used on all of the hardware and the containers that we use. Everything that we have is containerized. And then we have distributed tracing, see what's going on across the services, as transactions happen, what is going on. We collect them as close to the generation as possible. Infrastructure metrics, what's going on the object store, what are on the hosts. Gluster we use RabbitMQ for our event bus and message bus. event telemeter, metadata telemeter. So we collect as much as we can. This is sort of a few of the dashboards that we can use. Oh, excuse me. You know, on here, we can select a number of different things that we want to look at. So we have great visibility into our system, and that allows a small team to juggle it. So current challenges is roughly out of 10 people, we have 4 that are working on systems and DC infrastructure. Our challenges are unforeseen changes, you know, like I said, VBI processing off Summit. There are multiple modes for each instrument. Occasionally we get data that we can't process. Oh, why? Because they changed the mode. They got it in a different way. Future challenges are going to be higher data rates as they change instruments. That's already happening. We have a limited footprint. We can't grow our physical infrastructure anymore. This sort of happened in the last year, where we're told by Colorado University that the space we have is the space we have, and that's it. So we're going to have to figure out where to put all of our data later on. And that's it.
Yeah, thank you, Bob, very much.